Are we living in a greenhouse? We will start answering this question by looking at studies developed more than a century ago. In the 19th century, the Swedish scientist Svante Arrhenius was among the first ones to theorize the effect that doubling atmospheric carbon dioxide would have on global climate. Based on the work of previous researchers including Tyndall, Arrhenius acknowledges the important role of trace gases found in the atmosphere in determining the radiative equilibrium between Sun and Earth. Even before Arrhenius, Fourier had claimed that the atmosphere acts like the glass of a hothouse, because it lets through the light rays of the Sun but retains the dark rays from the ground. The important contribution of Arrhenius is therefore that he argued that variation in trace constituents of the atmosphere, namely carbon dioxide, could influence the temperature of our planet. So, to the question, are we living in a greenhouse? The answer is definitely yes. The basic physics of global warming is thus the radiative equilibrium between the Sun and Earth once the optical properties of the atmosphere have been also taken into account. The main greenhouse gases are water vapor, carbon dioxide, methane and nitrous oxide. They are able to absorb solar radiation, especially the long-wave part of it, and with well-defined absorption bands. The relative contribution of a substance to the greenhouse effect depends on its concentration in the atmosphere and its optical properties. A global warming potential, GWP, is conventionally assigned to each substance in the atmosphere, whether gases or aerosols, based on its radiative forcing, Rf, and its persistency in the atmosphere. According to the Intergovernmental Panel on Climate Change, IPCC, radiative forcing is the net change in the energy balance of the Earth system due to some imposed perturbation. It is usually expressed in watts per square meter, average over a particular period of time, and quantifies the energy imbalance that occurs when the imposed change takes place. Each substance in the atmosphere produces a certain radiative forcing that is eventually leading to a temperature change on the Earth's surface. The temperature change is established in response to a given radiative forcing at the climatological tropopause. The condition of equilibrium climate response to radiative forcing is such that the energy balance is restored and no flux imbalance is observed. However, a certain temperature shift is eventually observed that means climate change has occurred. As mentioned earlier, the definition of global warming potential also takes into account the average lifetime of each substance that causes the greenhouse effect. The IPCC definition of the global warming potential is the time-integrated radiative forcing due to a pulse emission of a given component relative to a pulse emission of an equal mass of carbon dioxide. Methane stays relatively short in the atmosphere with an average lifetime of about 12 years. Nitrous oxide lifetime is instead about 120 years. Carbon dioxide persistency in the atmosphere can be much longer, as it has a much slower decay function. On a 100-year time horizon, the calculated global warming potential is 28 and 265 for methane and nitrous oxide respectively. Despite their higher GWP, carbon dioxide is by far the largest emitted greenhouse gas compared to methane and nitrous oxide. Therefore, it remains the most important contribution to radiative forcing. The next sensible questions to ask ourselves are to which extent variations of greenhouse gas can occur, which are ultimate phenomena, both natural and anthropogenic, responsible for such changes, and finally, which is the potential effect on the global Earth temperature. Before looking at the anthropogenic contribution to increased levels of greenhouse substances into the atmosphere, it is worth looking at the natural events that cause variations in their concentration. In the past, ice ages have occurred alternated to periods of warm climate during which life flourished. Nonetheless, abrupt changes of the climate conditions occurred as well. For instance, volcanic eruptions can result in large emissions of sulfur dioxide that eventually lead to formation of fine sulfate aerosols. The aerosols increase the atmospheric albedo, thus cooling the Earth. Hence, major volcanic eruptions can alter our climate as well as other natural phenomena like orbital forcing. However, the impact of human activities can have an intense effect, because greenhouse substances are emitted in a continuous way and over the last decades with ever-increasing rates. Overall, the total anthropogenic radiative forcing over the industrial era has been estimated between 1.1 and 3.3 watt per square meter in the last assessment from IPCC. An iconic graph that is widely used to show the trend of carbon dioxide emissions in the atmosphere is the Killing curve, recorded from 1958 at the Mauna Loa Observatory in Hawaii. The annual oscillation of about 5 parts per million that is observed in the curve is due to the vegetation growing cycle. Indeed, carbon dioxide uptake from plants is maximum during spring and summer, while during fall and winter the respiration process prevails. Despite the inherent complexity of climate, there is a large consensus among scientists in linking the increased carbon dioxide concentration in the atmosphere to warmer air. In fact, the Earth's average temperature increased about 0.5 degrees Celsius since 1961. If no action is taken, the Earth could become even warmer. Although uncertainties remain about possible scenarios of global warming, the potential of climate-related catastrophes is there. Therefore, risk assessment and mitigation strategies to tackle climate change are required. Currently, we observe that in the Arctic regions, the temperature rises more quickly than elsewhere. This effect is referred as the Arctic amplification. The resulting melting of glaciers is probably the most important signs of climate change that we can observe today, and a reminder of the strange paradox of the world energy question.